Alright, so in this video we go over section 3.3 implicit differentiation and applications to word problems which are called related rates. So first we're going to look at the method of implicit differentiation in order to find the derivative of a function of an implicit function, and then we're going to do the applications. Well, so before discussing the method um, of implicit differentiation, let's have an idea of what an explicit function is versus an implicit function. Well, here on the left part of this box, I have a few implicit functions. Well, what do we mean by implicit function? An implicit function is a function that is not solved for the dependent variable. For example, typically y is the dependent variable and x is the independent variable. You know, the x represents the input or the domain and y represents the output, which is the range of the function. And in some cases, it is possible to solve those functions for y, and then we would have an explicit function. Let's see what can we do in which cases it's possible and in which cases it's not possible. For example, let's look at 5x plus 2y equals to 3. Well, notice that function right here is not solved for y. So, well, let's see if we can write this function, this implicit function, into explicit form. Well, in other words, let's see if we can solve for y. That is 2y equals, well, first we would need to subtract 5x on both sides. All right, that's to get 2y equals 3 minus 5x. Okay, so to get y by itself, all we need now is to divide both sides by 2 to get the following. Well, in this case, it is possible to get y in terms of x, that's 3 halves, minus 5x over 2. So that's the explicit function. In this case, it's possible to solve for y with no issues. Okay, what could be the issues? Well, you'll see in a minute. Let's look at another example of an implicit function, and let's see if we can write this in an implicit function, and let's see if we can write it in explicit form. So number one, let's try to solve for y by first subtracting x squared on both sides. And that's going to lead us to e to the y equals to 5 minus x squared. All right, well, in this case, to solve for the exponential, we need to undo the exponential. Well, in this case, we undo the exponential by doing the inverse operation to the exponential, which is to take the ln. Okay, so in this case, ln and exponential cancels. And in this case, it is possible to get y by itself, which is the ln of 5 minus x squared. Okay, so that's the explicit function. Now, let's observe this third case. For the third case, x squared plus y squared, well, that's the circle of radius 1. How do we know that's a circular function? Well, we have both variables squared with a plus in between. Well, that one tells us that the radius is 1. Let's see if we can solve for y in this case. Well, number one, so we need to subtract x squared on both sides to get the following, to get y squared equals 1 minus x squared. Now, when it comes to solve for y over here, there is an issue here if we want to get x by itself. So if we want that, we would need to take the square root of both sides. Well, the problem here is this plus and minus right here. So the issue then is that we would have y1 equals to negative root of 1 minus x squared and y2 equals to 1 minus square root of 1 minus x squared. So in this case, we have essentially two different outputs for the same input. And because of this plus or minus right here, that's an issue there. So for that reason, we cannot express that equation of a circle in terms of an explicit form. So we'll leave it in implicit form. All right, now let's see how do we find the derivatives of implicit functions. Well, so we have the first equation here. Okay, it's another circle of radius 5. They're asking us to find, number one, the derivative with respect to x, and then evaluate at the point 4, 3 and 0, 5. In other words, they're asking us to find the value of the slope at the point where x equals 4, 3 and y equals to 3 and x equals to 0, y equals to 5. So they're asking us to find those values of the slope. Well, look at the value at 4, 3. It's a negative slope, so the derivative, we can anticipate that its numerical value will be a negative number, as opposed to the value of the derivative at the point 0, 5, which in this case, look at its horizontal. And well, what's the value of the slope when of a horizontal line? Well, you guessed right, that's a 0. Okay, let's see if that is the case. So how are we going to take the derivative of an implicit form? It's usually the same. It's actually the same rules, the general power rule, product rule if necessary, quotient rule, all the rules that we have learned so far, and with a very particular with a particularity here that when we differentiate anything that contains the y, we need to multiply by dy dx. I'm going to explain that in a second. Why do we do that? So let's go ahead and let me rewrite the function. So in this case, well, let's take the derivative of x squared. The derivative of x squared is 2x. The derivative of y squared is 2y. But every time we differentiate a variable, the variable y, because this we are essentially doing a chain rule. So we are multiplying. So we need to multiply by dy dx. Well, where is that chain rule coming from? Well, the derivative of 25 is 0. So for example, think of the following. Like you think of the following, this y is a function that actually depends on x. So just like what we did in the previous section about the chain rule, you can think of this as a composition function. You know, you can see it as a composition function for which the inner function is x and the outer function is y. So when we take the derivative of y, we do the derivative of y, which is of y squared, which is 2y, then we need to multiply by the derivative of this function that depends on x. So that's why we're doing this mini chain rule. All right. So another way to explain why don't we multiply by dy dx on the x term? Well, let me do something on the side real quick. Let me redo this problem. X squared plus y squared equals to 25. So for example, for the second term we multiplied by, we got, 2y times dy dx. Okay, because this y is changing with respect x, because y is the dependent variable which depends on whatever x changes. So now what if we wanted to do the same for x? Well, 2x, but x changes with respect itself x. Well, look at this. What happens with dx over dx? Isn't that 2x? Doesn't that reduce to 1? 1 times 2x, that's 2x. 2y dy dx equals to 0. So that's another way to explain why do we multiply this dy dx when we multiply, when we differentiate rather a y, and not when we differentiate an x. All right, so now we're essentially done with the calculus here. Now the next step is to solve for dy dx. We need to isolate this because we want dy dx. All right, so the remaining part of the problem is just algebra. So let's subtract 2x on both sides to get cancel, 2y dy dx equals to negative 2x, and divide both sides by, let's divide both sides by 2y now. Okay, so cancel 2y with 2y, and dy dx equals, cancel these 2's, and we simply get negative x over y. So now the derivatives of implicit functions will contain both variables x and y, as opposed to the derivatives that we have done so far for implicit functions. Now, they're asking us to evaluate the derivative of the point 4 comma 3 and then at the point 0 comma 5. So let's go ahead and do that part. Okay, let me draw a little line here to do that part here. So the way we denote this is dy dx evaluated this little bar at the order pair 4 comma 3, and all we have to do is, okay, negative x, which is 4 over 3. Well, that's all we have to do. So it's negative 4/3. In fact, you can see the negative slope right here of this line. Okay, let's do the same for the derivative with respect to x evaluated at the point 0 comma 5. Well, x equals to 0 and y equals to 5. This is 0, and we can see that slope of 0. It's a horizontal line, all right, as we expected. So that is our first problem, a very simple problem in which we introduce the method of implicit differentiation. Let's apply this method to other more complex situations in which, like this one, example 2, notice here we are going to combine two different strategies of differentiation. Number one, notice we have on the first term the product of the functions x and y, and then we have another product of the functions x squared and y cubed. So we are going to differentiate each term using the product rule, which would be great to to recall what the formula is. So the derivative with respect x of the function f and g. Recall that there were different ways to denote this derivative. You know, that's one that I'm going to use is f prime g plus g prime f. That is the derivative of the first factor in the function times the second without doing anything, plus, rather, the derivative of the second function times the original first function. So let's see. Let's apply this product rule to the first term right here. Okay, so I'm going to differentiate x, and well, let me rewrite the function again. Xy plus x squared y cubed equals to, minus 1 equals to 0. So the derivative of the first product will be the derivative of x, which is 1 times y, plus the derivative of y. The derivative of y will be simply 1, but because we are we are differentiating a y, we need to multiply by dy dx. So that's the derivative of y times the first factor, which is x. Okay, again, if you want to label this, this is f prime g, and this is g prime f. Okay, that's basically the product rule applied to this implicit differentiation. Let's do the product rule for the second term, plus the derivative of x squared, which is 2x times y cubed, plus g prime, which is the derivative of y cubed, that is 3y squared dy dx, because we're differentiating a y, times x squared. Okay, again, what are we doing here? Let me use a different color. This is our f prime g. This is our g prime f. Okay, something, yeah. And I'm getting a little lag here. I don't know why. Okay, all right. Erase this, and that's f. All right, so that's the product rule again. And then don't forget to differentiate this -1. The derivative of -1, which is the derivative of a number, is plus 0, and on the right hand side we get a 0. The derivative of 0, well, it's also a constant, well, it's also 0. So let's do a lot of the cleanups here. So let me clean up parentheses, let's clean up multiplications, and you'll see what we're gonna do. So 1 times y, that'll be y plus x dy dx. So I'm writing this x right here in the front. That's the only thing I'm doing. Plus 2xy cubed, plus 3x squared y squared dy dx equals to 0. Now, because again we want to find dy dx, we want to solve for this dy dx. So what we're going to do, we're going to move all the terms that do not contain a dy dx, that is actually only this term right here and that term. Those two terms, I'm going to move them to the right hand side of the equation by number 1. On the one hand, by subtracting y on both sides, and by subtracting 2x y cubed. Okay, so let's cancel those terms and get x dy dx plus 3x squared y squared dy dx equals to -y minus 2x y cubed. And well, we want to solve for dy dx. So again, let's keep highlighting what I want to solve for. So I want to solve for this. And notice, okay, so the idea of leaving these two terms that contain the dy dx on the left hand side is to make a greatest common factor out of it. So we factor that GCF essentially. Dy dx, and that's an x plus 3x squared y squared equals -y minus 2x y cubed. And well, we're only one step away to get this done. In other words, all we have to do is divide both sides by x plus 3x squared y squared, divide by x plus 3x y squared. We are essentially done finding this derivative. So dy dx then I'm going to move over here and dy dx equals negative y minus 2x y cubed over x plus 3x y squared. Final answer to this question. All right, so let's see. We could leave it like this, that is fine. However, another optional way to express this result is by essentially factoring out this negative sign. Notice that that negative is common to both terms. So an alternative would be negative in the very front, y plus 2x y cubed, and divided by x plus 3x y squared. Either way is fine. So just alternatives for essentially solving the same problem. All right, let's do one third example. So let's find the derivative of the square root of x minus the square root of y equals 16. Well, so let's see what about it. Okay, so we recall that we cannot take the derivative of a radical just like this. So we need to first of all express this as rational exponents. Okay, and then from here we're good to go and differentiate. So taking the derivative of x to the 1/2, that is 1/2 x to the negative 1/2 minus 1/2 y to the negative 1/2. But recall that when we differentiate a y, because that y depends on x, we need to multiply by dy dx. Essentially, we're doing a mini chain rule, taking the derivative of the inner function, which is a function that depends on x pretty much, and the derivative of 16, that's a 0. Okay, so number one, let's see what can we do about it, because we have a combination of both negative exponents and we also have fractions. Well, so number one, this is what I will do. So on the one hand, I'm going to move, well, because ultimately we want to get the dy dx by itself. So what we're going to do, we're going to send all the remaining terms that do not contain a dy dx to the right hand side. In other words, this term. So let's see. We're going to subtract 1/2 x to the negative 1/2 on both sides. And well, so from here, cancel, and negative 1/2 y to the negative 1/2 dy dx equals negative 1/2 x to the negative 1/2. Right, so that's what we get to when we try to solve for x over here. Now, here is where things get a little bit tricky. Well, number one, I think I'd rather get rid of two things at the same time. Number one, the fractions, the 1/2 and the negative. So in order to do that, I'm going to multiply both sides by -2. So in this case, that's going to leave us with y to the negative 1/2 dy dx times dy dx equals x to the negative 1/2. And to get dy dx by itself, all we have to do now is divide by y to the negative 1/2 on both sides of this equation. So let's see. Cancel, and dy dx will be x to the negative 1/2 over y to the negative 1/2. And well, you might want to clean this up a bit further. Yes, it's possible. Well, recall that this negative exponent indicates that we need to send it to the denominator with positive exponent. We send the x as we send it as x to the 1/2. Just the same way, because of this negative exponent in the denominator, that indicates that we should move it to the numerator with positive exponent. Let's go ahead and do that. And that is, that will be dy dx y to the 1/2 over x to the 1/2. All right, now we can simplify this a bit further. Of course we can. And notice that both y and x contain the same power. That is 1/2. That is going to be y over x to the 1/2 by the following property of exponents or law of exponents. When you have a over b to the m, or rather a to the m, b to the m, the law of exponents here, a over b, the whole thing to the m power. So that's essentially what we're doing from here to there. All right. So, and then last but not least, take the derivative with respect to x. Well, let's write it. Anything to the 1/2 power means square root. And we're done with this problem. Alright, so these were a couple of examples for which we take the derivative using the method of implicit differentiation. That is, taking derivatives of functions that cannot be written in implicit form. Well, maybe this third example it's possible. However, if you try the second example, try solve for y, you will find out that it wouldn't be possible to solve this for solve for y in an explicit form. The next topic on this section is applications to word problems using the method of implicit differentiation and chain rule combined. However, I'm going to leave that for a second part of this section. I'll see you in that video.